Oh, hi there. You scared the crap out of me. So, you're here because you want to learn a little bit more about capacitors, huh? Well, I've been pretty busy lately. And this may mean that I'm going to have to add another 10 or so months before I get to your next physics lab, get that all graded and everything. But hey, what the heck? Let's talk capacitors. Let's go for it. Come on. Alright, let's say I've got a parallel plate capacitor. The very top is charged to plus Q. The bottom is charged to minus Q. I want to use Gauss's law to find the electric field strength in between these two plates. And then I want to figure out what is the potential difference from one plate to the other. So we already did the example of a single charged plate. We made a Gaussian surface that was like a rectangular prism, I think it was, or a cube. Alright, so there's my cube. Now, it has a bottom, a top, and 4 different sides. So if I wanted to find the total flux passing through it, I would need to add up the flux from the top, from the bottom, and from the sides. Here's one thing that'll be helpful. Because the electric field is perfectly vertical, and my sides are vertical, that means my sides would have area vectors pointing perpendicularly away from it at all points. That means that the angle between the area vector for the sides and the electric field is going to be 90 degrees. And the cosine of 90 degrees is 0, so the flux going through the sides is 0. Also, if you remember our expression for the electric field around a single plate, it was this. And that just came from doing Gauss's law with just one plate. But one thing that we discovered was that the electric field does not depend on the distance away from the plate that you're measuring it, as long as the distance is small compared to the area of the plate. Well, here's what that means practically for us. The electric field here is going to be going completely vertically downward away from the positive plate and toward the negative plate. When we had just a single plate, we also had to deal with electric fields passing up through the top this way. However, in this case, we'd have an electric field from the top plate going in that direction, but we'd also have an electric field from the bottom plate going in the opposite direction because the bottom plate is negative. And since the field strength doesn't depend on the distance away, it doesn't really matter that that negative lower plate is farther away from this location. These two fields are going to cancel each other out. And so all I'm left with, once I realize I have 0 electric field going through the top surface of my Gaussian cube, all that I've got to handle is the flux going through the bottom. So all of a sudden, looking only at that bottom surface of my Gaussian, I'm going to have the integral of the electric field with respect to area equals Q enclosed over epsilon naught. All right, so a couple of things to notice at this point. One, the charge enclosed is not the full charge on the plate. I'm only enclosing a portion of that plate with my Gaussian cube. I have to because around the edges, I start to get a little bit more of a dipole pattern like you all created when we formed our human electric field. So because of that, I've got to keep my Gaussian cube smaller than the area of the plate itself. So let's go ahead and say that it has sides L all over the place. Since all I care about is this little bottom face, since that's the only direction that the electric field is passing through parallel to my area vector, that means the area of the Gaussian, which is what's happening on the left-hand side, it's just going to be L squared. Now let's look at this Q enclosed thing. Q enclosed. Well, since I didn't enclose the entire charge, I've got to use this idea of charge density again. Since we're dealing with basically just a two-dimensional plate, let's go ahead and call sigma, I could refer to it as the total charge divided by the total area of the plate, or I could refer to it as the enclosed portion of the charge divided by the enclosed area, which would be L squared again. Notice over here, when I evaluated the surface integral, I only included that one face of the cube. Again, that's because it's the only one that had electric field flowing through it. When we previously did this problem, we had a little 2 snuck in here because we were worried about the top and bottom faces. Now it's only the bottom face of that cube that's getting it. Same thing over here. On the charged plate itself, the area constraining the enclosed charge is simply L squared. Okay, so I can solve for Q enclosed. That's just sigma times L squared, and then I can replace it in this equation. And per usual, it doesn't matter the size of the Gaussian I created because it all cancels out right here. So what I'm left with is the electric field equals sigma over epsilon naught, or I could replace sigma with Q over A, the full charge on that plate divided by the full area of that plate. This is no longer about my Gaussian surface. This is about the size of the plate itself. And so there's the expression of the electric field between 2 plates of a parallel plate capacitor. Notice that it only depends on Q and A and the constant epsilon naught. So once you have your capacitor established, have it fully charged up, then the electric field between the plates is constant at all locations between those plates. Getting to deal with a uniform electric field makes a lot of other calculations a good deal easier as well, such as trying to find the potential difference between the plates. And that's what we're after right now. From an earlier lesson, we know the potential difference is simply the negative integral of electric field with respect to distance. So let's go ahead and figure out the bounds of integration here. We're going to integrate from the bottom plate to the top plate. Let's go ahead and declare this to be a height of 0. Let's go ahead and I'll put r in here. R equals 0, and then let's say it's some distance d. A lot of times the plate separation is denoted by little d there. So if we're going from 0 to little d, and we're integrating in the direction opposite the direction of the electric field, that means the angle that we're worried about here, if my r vector is up and the electric field is down, the angle is 180 degrees. And we know that the cosine of 180 degrees is simply -1. So I've pulled my constants out of the integral. E is a constant, cosine of 180 is a constant. In fact, because the cosine of 180 is -1, this is just going to become E times the integral dr. And I can substitute in my expression for E that I found right over here, Q over A epsilon naught. This will be Q over A epsilon naught times the integral of dr. Oh, right. I had discovered the bounds of my integration, and I forgot to put them in here. So the bounds are from 0 to d. There we go. So this will be Q over A epsilon naught times d minus Q over A epsilon naught times 0, which just comes to 0. Okay, so let me start fresh, rewrite this a little bit more neatly. Delta V equals QD over A times epsilon naught. Now, one thing we know about capacitors from the definition of capacitance, it's that Q equals C times delta V. So let me replace delta V with Q over C. And what I end up with over here is Q over C equals Q times D over A epsilon naught. Oh, and my Q's cancel out. I'm going to go ahead and multiply my C up to the other side of this equation here, and then I'm going to multiply the reciprocal over to this side. And what I end up with is, oh, look at that. That is the exact same equation that I gave you at the start of this lesson. Man, isn't physics and math fun? Wow. That explanation took so long, I'm in completely different clothes right now. Whew. Another day gone. Guess I'll have to add an additional 20 days to my estimate of when I'll get your lab back to you.